So we're doing activity 3, and it talks about our sort of generic mechanism sequence, right, where we're doing nucleophilic acyl substitution reactions. At a minimum, we need a nucleophilic attack on the carbonyl carbon, and then loss of a leaving group. And then sometimes there are other proton transfers, either prior, in the middle, or at the end of those required steps. And so it's going to be our job to determine when those are necessary and when they're not. And the proton transfers, I mean. And so we're going to look at esters first, and we're going to be doing, the first one is basic hydrolysis of an ester, and then the next one is acidic hydrolysis of an ester. So you can hydrolyze an ester 2 different ways, through using a aqueous base or aqueous acidic solution. And by the way, don't forget, I do have YouTube videos going over the mechanisms of these. So if you need an extra video to watch, those are there for you. Okay, so when we have a initial reaction, initial nucleophilic attack, we need at least one of the 2 components to be considered strong, right? So either a strong electrophile and or a strong nucleophile. The ester is considered one of the weaker electrophiles. So the carbonyl carbon is pretty stabilized by the oxygen's lone pair. It's not very reactive. So I would say this is a weaker electrophile. Remember, the acid chloride and the anhydride are the 2 stronger electrophiles of the carboxylic acid derivatives. And also ketones or aldehydes are fairly strong, but they're not a carboxylic acid derivative. So we're not really talking about those in this chapter. But esters and amides, those are the ones that are a little bit more stable. But however, we are reacting it with hydroxide as a nucleophile, and hydroxide is a stronger nucleophile. And so that actually makes up for the fact that we're using one of the weaker electrophiles. So because we have a strong nucleophile, we don't need an initial proton transfer to make this a stronger electrophile. So we are just going to show the nucleophilic attack on the carbonyl carbon, right? So this one is the nucleophilic attack, and the resonance arrow to form what they sometimes call the tetrahedral intermediate, because this carbon went from sp2 in planar to sp3 and tetrahedral. And at this point, we could either regenerate the carbonyl and kick out hydroxide or the alkoxide. Neither one of those are considered great leaving groups. However, they can be strong enough under basic conditions to leave. And if we were to kick out the hydroxide, it would just go straight back to the ester. And then eventually it might be also possible to kick out the alkoxide instead of the hydroxide. They're basically equivalent in terms of leaving group. So the hydroxide and the alkoxide are about the same strength or have about the same ability as a leaving group. So it doesn't really matter which one you kick out. You either kick out hydroxide and go back, or kick out an alkoxide and go this direction. So we're going to kick out the alkoxide and see what happens, right? And when we do that, we've kicked out the alkoxide and we've generated a carboxylic acid. So that's really important, because one of the things that we know about the carboxylic acids are that the hydrogen here is acidic, right? So this hydrogen is a pKa of approximately 5. And so we've now generated a fairly strong acid in solution. And we're in a solution with hydroxide, and we've just kicked out the alkoxide, right? So we have an acid in the presence of a strong base. So there's going to be an immediate proton transfer here. So in kicking out the alkoxide, we actually form the carboxylic acid, and then there's an immediate and essentially irreversible proton transfer at the end. So that's what we call the driving force of the reaction, because all of these steps up to that point were reversible. And then all of a sudden we have this irreversible step Why are we saying it's irreversible? When you compare the pKa of the acid, which is 5, and the pKa of the conjugate acid, right, which is about 16, there's a difference of 11 pKa units, right? So there's 10 to the 11 more products than reactants. So it's essentially irreversible reaction. So this drives the reaction forward to the point where now we can't go back to the ester anymore. Okay, so once we're at this carboxylate though, in order to isolate the carboxylic acid, we would need an acidic workup, right? So this must undergo an acidic workup in order to isolate the carboxylic acid, because right now we're under basic conditions, right? So the acidic workup, at the end of the reaction, you would dump in a bunch of aqueous acid and you would protonate the carboxylate, right? And you would be able to isolate the carboxylic acid. Okay. So just be careful, right, with this mechanism, because a lot of people will stop here. Because notice how after this second step, we have the carboxylic acid. So it seems like we're done, right? Because the product is a carboxylic acid. And we generated the carboxylic acid in the second step. So it's like, I'm done. But it's not really true. If this was the case, this would be an equilibrium controlled reaction. Under basic conditions, there will be a proton transfer and you need an acidic workup in order to actually isolate the carboxylic acid. Okay, so we did not need an initial proton transfer because hydroxide is a strong enough nucleophile. We did not need any proton transfers before loss of a leaving group, right? So the second step was loss of a leaving group. And that's because under basic conditions, these are acceptable leaving groups, hydroxide or the alkoxide. But at the end, we had some proton transfers just because of the fact that we generated a carboxylic acid in strong base conditions. So there will be a deprotonation that occurs, and you have to do an acidic workup to reverse that. Okay, so let's look at the ester hydrolysis under acidic conditions here, right? So there's usually a lot more steps under acidic conditions. Let's analyze, right? What is the nucleophile and what is the electrophile in this reaction if we were to do the required nucleophilic attack here, right, without any proton transfers. The electrophile is the ester, which we already know is a poor electrophile, and the nucleophile is actually water under acidic conditions, right? Because the best base we have in solution, if it's acidic conditions, is water, right? Because this is not a base or a nucleophile. So this is the best we have. So this is a poor nucleophile, water. Ester is a poor electrophile. They're not going to react without some help. Okay, so the activation energy is simply too high for those two stable things to want to spontaneously react with one another. So that's where the catalytic acid comes in, right? That is crucial. So what does the catalytic acid do? Well, it protonates. And some people ask me, well, can it protonate the oxygen of this group here, right? This oxygen attached to the methyl group, the other one, can it protonate here? And the answer is yes, it can, but it's also reversible. And it doesn't, nothing happens. You protonate the oxygen, nothing can happen. Okay, so it eventually deprotonates and something else happens. So the mechanism is not necessarily every single thing that's happening in solution, it's just the thing that actually progresses to make something else that's stable. Okay, so the acid, right, protonates. That's a proton transfer. By the way, these were both proton transfers. up here, which I did not label those. Okay. The acid protonates, and what does that do? That basically makes this entire ester electrophile more reactive, and specifically this carbonyl carbon more electrophilic, right? It makes it charged, so we know that anything charged is less stable than something that's not charged. So this is more stable than this just because it's not charged, right? And this is charged. So it's raised the energy of the electrophile, making it more reactive, and also making the carbonyl carbon more electrophilic. So now we actually have a strong electrophile. So once we have a strong electrophile, there can be a nucleophilic attack. And even a weak nucleophile, like water, can do the nucleophilic attack with the stronger electrophile. Okay, so that generates our what we call our first tetrahedral intermediate here. And then of course this is reversible, so just like water did a nucleophilic attack, it could come right back off, right? We could do loss of a leaving group and it would go right back to this. So that can happen, but it's also possible that the water in solution can deprotonate this and make this not as great a leaving group anymore. Right, so it's reversible, it's attacking, it's getting kicked back out, it's attacking, it's getting kicked back out. Eventually, perhaps something actually deprotonates it and makes it not as able to leave anymore, a lesser leaving group. This is our next proton transfer. Okay, and now we have something neutral. So this is kind of what we call our proton shuffle, right? We need this to be the leaving group. Right now, it's not protonated. We want to protonate it, but only after we deprotonate the oxonium, because that would prevent having two positive charges in the same molecule. So now that we have something neutral, we can go ahead and potentially add a proton to the OR group, the O methyl group, and that makes this now a good leaving group. Right? And once it's a good leaving group, then it can leave. And notice how I had two OH groups here, right? So either one of those could have done the pushing to kick out that leaving group. Okay, so this actually is our loss of a leaving group step. Okay, once we kick out that leaving group, right, it says minus methanol here. We're really close to the product. We just need to do a final proton transfer. We kicked out one molecule of methanol, but we're in a solution with a bunch of water. So it's more likely that water instead of methanol would act as the base to do the final proton transfer. So that's why they drew it as water and not methanol, but it could be either. It's just probability-wise, it's probably going to be a water molecule. Okay, so he wants us then to think about what the purpose was, right, of each of these proton transfers and write something about that. So the first proton transfer, that's this one, and this is the second, the third, and the fourth, right? Proton transfer. So the first proton transfer, it, you could say it creates a stronger electrophile. Okay, which is more reactive due to being charged in higher energy. It also lowers the activation energy for the nucleophilic attack. So lots of explanation there. Okay. What is the purpose of the second proton transfer? Well, proton transfers are happening all the time in solution. Basically, Notice how all the positively charged things are oxygen. So at some point, all of the oxygens have or don't have a proton to be neutral or positively charged. So proton transfers are really occurring all the time, but you could say that the point of this is to lower the propensity of this water to act as a leaving group, right? So you could say to lower the ability of water to act as a leaving group. Okay, and that essentially moves the reaction forward. Okay, so the next one, the third proton transfer, that creates the methoxy group, makes it a better leaving group. So makes the OR group a better leaving group. Right, because it can't leave and become negatively charged in under acidic conditions. And the last proton transfer, the point is to generate a neutral product, right? Maybe. So a neutral, let's say, stable product. Okay, I don't know, it's kind of weird to think about the point of all the proton transfers, but I guess that's what I would say, the point of that one. Okay, the next part of the activity is talking about reactions of formation of esters. So how can we make an ester? Well, in this chapter, there's 3 reactions introduced to make an ester. 2 of them are from carboxylic acids, right? These are from a carboxylic acid, and then one of them is from the acyl halide. The acyl halide reaction we learned in the last activity, right? If you treat a acyl halide or really an anhydride, wouldn't matter. Although anhydrides are just less talked about and less worried about, I guess. With an alcohol, right, you can get an ester. And pyridine is optional to prevent the formation of HCl as a byproduct. So that's one reaction we talked about last time. And then we also have the reactions of a carboxylic acid. So under both acidic and basic conditions, we can form an ester. Under acidic conditions with an alcohol and acid, we actually have a name reaction for this one. This is called the Fischer esterification. So that takes the carboxylic acid, an alcohol, and an acid catalyst and forms an ester in water. The Fischer esterification, by the way, is reversible. So if you take an ester, water, and an acid catalyst, you can get it to go back. So how do they favor one direction or the other in terms of reversible reactions? Right, notice the reversible arrow here. That's more about the concentration of the reactants. So for example, if you wanted to go this direction, you might have a lot of methanol around or a lot of the carboxylic acid to drive the reaction forward. In the reverse, you would have a lot of water around, so a very dilute acid solution would make it go back. Okay. So there are ways to control the equilibrium in reversible reactions. And then the other one from a carboxylic acid is to simply use a strong base that will deprotonate the carboxylic acid to make it a carboxylate, which will then undergo an SN2 reaction with an alkyl halide. So this would be most preferably methyl or primary because it's an SN2 reaction. Right? The second step is, so most preferably methyl or primary to generate an ester. So one of the advantages of the Fischer esterification is you don't need to use a methyl or primary alcohol. You can use pretty much any alcohol. Okay, and with this reaction, we are relying on an SN2 reaction where the carboxylate does an backside attacks and kicks out the iodide. So we have to have methyl or primary. So that's a bit of a difference there. Okay, so let's look at some strategies to make these esters. Right, so we have, you can see that sort of this side is the carboxylic acid side, right? And then this side is the R group side. Okay, so if we're starting, two of these reactions start from a carboxylic acid, the first two, right? So we want to figure out what side was the carboxylic acid. So we will go ahead and draw that. So in this case, we're starting from cyclohexane carboxylic acid in both cases. And we can either do the acidic conditions or the basic conditions. Right? So we can, under basic conditions, you would use a strong base. Sodium hydroxide is strong enough to deprotonate a carboxylic acid. And then you would need to use this as an alkyl halide, the R group. So this is actually not a very good reaction, right? Because this is not methyl or primary. This is a secondary alkyl bromide, right? So this is, we'll just kind of put secondary alkyl halides, not ideal due to SN2. Okay. So that is one option, although it is not a very good option in this case. Our second option would be to add in the alcohol and acid, right? So we could do an acid catalyst and then have the other component be an alcohol. This is a much better option for this particular case. And then the other option is to have started with an acyl halide. Oops, I don't know why I'm drawing double bonds in there. Got excited, wanted to draw aromatic ring. Okay, so we have the acid halide and the alcohol, right? Remember, pyridine is optional. So we'll draw our little alcohol in here and maybe add some pyridine. Okay. And that would also make the ester. Okay, this one is a little bit more challenging, right? Because the it's intramolecular reaction here. So we're going to be making this bond, but this is the carboxylic acid side. Okay, so how about we draw the carboxylic acid? Okay, and then we think about how many methylenes, right? So 1, 2, 3, 4. 1, 2, 3, 4, and then a if you were doing the basic one, this would have to be a halogen. Okay, so perhaps we're out of bromine there, and then reagent would be sodium hydroxide. Okay, so this would be deprotonation of the carboxylic acid, and then it would cycle around and do an SN2 to kick that out. Does that make sense? So to form the ring. So we'd form the carboxylate by deprotonation, then it would basically do a backside attack here to kick out that bromine. If you were going to do an, yeah.
Sorry, just is the reason for that reaction that the OH in our reagent, the NaOH, wouldn't do SN2 just because it's,
yeah, so
I don't know.
Proton transfers are generally faster reactions than other organic reactions because basically it has to do with the transition state. In order for hydroxide to do the reaction, it would have to come in perfectly from the back to and orient itself that way to do a reaction. So those just happen a little bit slower just because of how often that sort of collision occurs. But proton transfers tend to be very fast compared to other steps. So So it's much more likely with an acidic proton around that the hydroxide will act as a base to deprotonate this rather than a nucleophile to do it.
Oh, okay. So it's the hydroxide is kind of busy doing other things.
It can do both, right? It's both a strong nucleophile and a strong base. And with an acid with a pKa of 5 around, it's going to pretty much immediately deprotonate that.
Okay.
Because it's just going to be it can collide with that proton from any orientation. So is it possible that it does some SN2? Yes. And that's probably a byproduct of the reaction. It's just that it's much more likely to do this. And also you have another alternative. If that turns out to be a big problem, right, then that's why we have multiple ways to do kind of the same thing. So instead, let's say you added it and you saw, oh my gosh, it did exclusively SN2. What would you get, right? You would get this product from that. And then as a chemist, you would go, okay, that didn't work, right? What else can I do? Oh, I can do a Fischer esterification, right? So then I would take that product and I would go ahead and mix it with some catalytic acid, right? And then I would probably do something to absorb the water that's formed to drive the equilibrium forward to form that product. So there are ways to remove water as it forms in a reaction, and that would essentially, through Le Chatelier's principle, drive it to forming the ester. Okay, and then we also have the alcohol and the acid halide or acyl halide option, right? And you could just literally, this would react probably with no help at all, but you could add some pyridine. So as soon as the acyl halide is formed, it would probably immediately react with the alcohol. But if for some reason it didn't, you could always mix it with some base and it would work. Okay. Next part, filling in the boxes. Okay, so we're doing a Markovnikov hydration reaction. And in this case, we do need to worry about rearrangement. So acid is not the best choice. And we would prefer to do oxymercuration, demercuration. Remember, we have two options here. And this is used in cases where a carbocation is formed that would probably rearrange. In order to convert this alcohol to an alkyl halide, you might think to use HCl, but again, HCl would probably involve forming a carbocation here, which would rearrange. So I think SOCl2 is a better option to avoid rearrangement. So this is our converting an alkyl halide to a carboxylic acid by adding a carbon reaction. So we would do a Grignard formation for this. Remember, the Grignard is a little bit better here than sodium cyanide just because it's a secondary and more sterically hindered alkyl halide. Okay, so the next step is forming a ester. Because of the R group here, so notice I'm going to circle this isopropyl group and call it the R group of the ester. Right, because that's a little bit bulky, I would probably prefer to do the Fischer esterification. So I'm going to use the alcohol and some acid, just because it's probably not ideal for the SN2 process. Reduction of an ester to a aldehyde uses DIBA, diisobutyl aluminum hydride. And then this is a sequence where we form the hydrazone through use of hydrazine. And followed by the Wolff-Kishner reduction, which uses aqueous, KOH, and heat. Okay. So next we have, and So we just went over how do we make an ester, right? The 3 different ways we learn to make esters through this reaction, through this chapter. And now reactions of esters to make other things, right? So we have some review reactions. So we know that esters react with Grignard reagents to form tertiary alcohols. They react with LAH to reduce down to a primary alcohol. Right, so those are some review. We also learned in this chapter that you could use diisobutyl aluminum hydride, or DIBA, to reduce an ester to an aldehyde. And we just learned about the reaction of a carboxylic acid to make an ester using acid or base. Remember I said the acid catalyzed reaction is reversible, the Fischer esterification. So this reaction is really almost the reverse Fischer esterification, okay, where we are going to be using probably an acid catalyst with a lot of water or a dilute acid solution to hydrolyze the ester back to a carboxylic acid. Okay, and we can also do a basic hydrolysis of an ester. And I think we did that mechanism on the first page of this activity. So we did both the acid catalyzed hydrolysis and the base catalyzed hydrolysis. The mechanisms for those two were on the first page, right? So we'll kind of say mechanisms, first page of activity. Okay. And then we can also make an amide using ammonia. So you could, for example, use ammonia and mix it with an ester. This reaction, however, I don't really like it very much. This is more of a slow reaction and probably requires some heat. Okay. And the reason for that is ammonia is not as strong a nucleophile as like hydroxide. So it's kind of a weaker nucleophile, and in esters we know are weaker electrophiles, so it has a high activation energy for this one. So it's not ideal. If you want to make an amide, it's much better to, for example, start from an acid chloride, right? Because that has a much stronger electrophile and the reaction with ammonia will be fast, right? So I would say better to make amides, or some people call them amides, from an acyl halide. That'll just be a much faster reaction with ammonia reacting with the acid halide instead of an ester. But it's possible that you could do it from an ester. Okay, so now we're going to be proposing some mechanisms where it says use the mechanism of the acid catalyzed hydrolysis of an ester in problem number 1 as a model and propose a mechanism for the acid catalyzed amide hydrolysis reaction. So we're going to basically be doing the same sort of steps, right? So I can draw out my acid because I know I'm going to be doing a initial proton transfer, right? Because think about, it's the same reasoning as before. Amides are actually the most stable and the nucleophile is water, right? So that's not going to do anything without an acid catalyst. So that's why we need the acid catalyst, and we're going to protonate the oxygen. Okay. Just like we did before. So that's going to make the amide much more electrophilic than it was before. Okay, so it can, now we can do our nucleophilic attack with water. We've reached our first tetrahedral intermediate. After the nucleophilic attack, notice that we are making a carboxylic acid, so we're eventually going to be kicking out this group here. Right, so we need to do a proton shuffle. We basically need to get rid of the proton over here and add it over there to make a good leaving group. Right, so we're set up to do that. We can just use a water molecule to deprotonate. Right, and then we can use some hydronium to protonate the nitrogen. Once we've protonated the nitrogen, we've generated a much stronger leaving group, because that nitrogen cannot leave before it's protonated, otherwise it would be generating a strong base under acidic conditions, which we don't do. Right, so once we've protonated that, now it's positively charged. And now it's a good leaving group. So we can go ahead and kick it out. Go ahead and use either OH group to push that off. We've kicked out our amine, our methylamine. There, that's a good leaving group. And basically water or the amine, whichever you want, can come in and do that final proton transfer. Technically the amine is a better base, but there's a bunch of water around, so it could be either. Okay, and that regenerated some of our catalytic acid. Okay, so basically very similar to acidic hydrolysis of an ester. The only difference really is the different leaving group. Okay, so we can also do basic hydrolysis of an amide, just like we did basic hydrolysis of an ester. So when we have a strong base, we don't need an initial proton transfer. This is now a stronger nucleophile as well, and it can react with the amide. Why do you think heat is necessary, right? It's because, remember that the carbonyl carbon of the amide is not very electrophilic. So even though this is a stronger nucleophile, we have the world's worst electrophile, right? So we actually do need some heat to even help this reaction occur at all. Okay, so what we will show that nucleophilic attack. By the way, you need heat in the acid, the acidic mechanism above. It doesn't say heat, but you need to heat it because amides are not very reactive. So it helps overcome a larger activation energy barrier. So both of them need to be heated. Okay, so that's our tetrahedral intermediate after the nucleophilic attack. And now we can kick out the leaving group with no proton transfers necessary. Can you kick out hydroxide? Yes, right, but eventually you might be able to kick out the amine, and that will generate a carboxylic acid, and an immediate proton transfer will be triggered, just like with the ester. So, right, if we kick out this is a leaving group instead of going back and kicking out hydroxide, right, then we get a carboxylic acid. which again with its pKa of 5, very acidic, right? Then as soon as you kick out your leaving group here, right, this is a strong base in the presence of a strong acid. There will be an immediate irreversible proton transfer that occurs. So this is the irreversible proton transfer. That gives you the carboxylate and the amine. So he has it stopping at the carboxylate, right? So we're basically done with the mechanism. However, if you did do an acidic workup, then you would introduce a bunch of hydronium ion, which would protonate that. So the acidic workup, even though it's not mentioned here, right, we can just note that you could do an acidic workup to get the neutral carboxylic acid. Okay, so essentially, right, I'm just going to say you could stop here, or you do an acidic workup. So then I think he asks, is there comment on the hydrolysis of amides when compared to the hydrolysis of an ester? Are there any similarities or differences? I would say that the mechanisms themselves, right, the mechanisms involve or have the same steps. So they're pretty much the same thing. I would say in terms of the reactions, right, of the overall reaction, we do have a different leaving group, and the activation energy will be higher for the nucleophilic attack on an amide compared to an ester. For nucleophilic attack of amide versus ester, so heating is required for amide hydrolysis. Or much more heating is required for amide hydrolysis compared to esters. Okay. So next we have reactions of amides, right? So we can do, just like in the last page, we talked about the acidic versus the basic hydrolysis of an amide, right? So these two were mechanisms we just covered. And if you do a basic hydrolysis, you need to do an acidic workup if you want to isolate the carboxylic acid. Okay. So even though it looks like this is H3O plus and this is H3O plus, they're really different meanings, right? This is just a H3O plus workup, which is just different than H3O plus and heat it for a really long time in the presence of acid. Okay. So there is heat needed here. This is actually a pretty challenging reaction to do in reality. Okay. Whereas this is just exposure of the carboxylate to acid during the extraction process at the end. Okay. You can also reduce an amide to an amine, which is useful. And you can convert an amide to a nitrile through use of thionyl chloride. So notice that we did not, it's the same number of carbons, right? So this carbon becomes this carbon. So we don't really gain or lose any carbons. So be careful of that. And just as I mentioned that, right, there's actually an error on the next part where it talks about nitriles, right? How do we make a nitrile? You can either do an SN2 reaction from an alkyl halide with a cyanide ion supplied from, for example, potassium cyanide. This is just the polar aprotic solvent for the SN2 reaction, DMSO. So don't really worry about that. Right? This is just a solvent that might be used. And then we also can, so this reaction up here that we just talked about, right? We can make a nitrile from a amide, but he accidentally added a carbon here. So note that the CN contains a carbon, right? So we actually added one. That was a mistake. So this is actually a dehydration. We lose water in this process, but we don't gain or lose carbons through adding thionyl chloride. There's no carbons in that molecule at all. So it should look like this. Okay. So basically the reason why I point this out, right, is because it's carefully you want to think about, okay, I need to make a nitrile. Do I want to add a carbon or not? Right? The SN2 reaction adds a carbon, so it's a 1 carbon homologation reaction. Whereas the dehydration from the amide, right? So no carbons are added. So it depends on if you're synthetically, if you need to add a carbon or not, which pathway you might choose. Okay. All right. And then the reactions of nitriles. So what can you do from a reaction? So remember that this chapter just has a million reactions, right? So make sure you're using your flashcards to learn all these. Okay, so what can we do? We can do acidic or basic hydrolysis to get back to a carboxylic acid. So really this is not different. You could do acidic or basic hydrolysis of an ester, of an amide, and now also of a nitrile, right? So they're really very similar processes. And they all give you, no matter if you start from the ester, the amide, or the nitrile, you always get the carboxylic acid. So basically, you can always go back to the carboxylic acid through acidic or basic hydrolysis. And this reaction, the nitrile, first produces an amide, which then gets hydrolyzed to the carboxylic acid. So it actually goes through an amide intermediate. So first we convert the nitrile to an amide, and then you can convert that to a carboxylic acid. And if you want to see those mechanisms, don't forget about my YouTube channel. I have all of these in a playlist. Just be careful that I usually use edition 3 of Klein, so you would want to look at, instead of chapter 21, it's actually chapter 20. But you can find all of those hydrolysis mechanisms in that playlist. Okay, and then this is a really interesting reaction. I like this one a lot, okay, because we can go directly from a nitrile to a ketone. That's actually really useful and kind of cool, because usually if you use a Grignard reagent, it adds more than once, right? So think about when you use a Grignard reagent on an ester, what happens? It generates the ketone, then reacts with the Grignard reagent again and makes an alcohol. When you start with an acid halide, what happens? Right? You use the Grignard, it attacks the acid halide, chloride leaves, and then you get a ketone, and then the Grignard attacks the ketone. So your alarm bells should be going off when you see this reaction. You're like, what is happening here? Because how are we isolating a ketone in the presence of a Grignard reagent? That's weird, right? We know ketones react with Grignard reagents. So why isn't this ketone getting attacked with a second Grignard reagent, just like it would if I had started from an ester, if I had started from an acid halide? Okay, so that's kind of weird. So what is the explanation for that? Right, so the nitrile, the carbon is electrophilic just like a ester or an acid halide. And the Grignard reagent, right, can do a nucleophilic attack on the carbon. So what does that form? Right, so that actually forms, I should call this R1. Right, so I'll call this R1. So it actually forms a intermediate that looks like this, okay, with a double bond to nitrogen. And then it's stuck like this. Why is it stuck like this? It's stuck like this because there are no leaving groups, right? If we try to use this lone pair to regenerate the triple bond, we can't kick out either of those R groups. This is not a reversible reaction. There's no leaving group, so it's stuck like exactly in this intermediate. Nothing can happen. And then what do you do with a Grignard reaction? What sort of workup do you do? Right? This is what that second step here is for, the acidic workup. So it's basically stuck, right? There's no leaving groups. Nothing that act as a leaving group. Okay. And then you do an acidic workup, right, where you add in a bunch of H3O plus. So what's going to happen when you add in a bunch of H3O plus? Well, you're going to protonate the nitrogen, of course. And what did you form? Anybody recognize that? We form an imine. And what do we know happens to imines in the presence of aqueous acid? Right? They get hydrolyzed. So imines under H3O plus reverse back to the ketone, to the carbonyl. But this is not happening until there's no more Grignard around. So basically the imine and then the carbonyl are not exposed until the workup. They're not formed until the workup. But what has happened to the rest of the Grignard reagent? As soon as I add acid, it's gone, right? It's going to protonate the Grignard reagent. There's no Grignard reagent left. So we don't actually form anything that could react with the Grignard reagent until the Grignard reagent is quenched in the reaction anyway. So very interestingly, we can actually isolate the ketone and it won't react with any Grignard reagent. So that's a very unique reaction for a carboxylic acid derivative. Okay, and you can also reduce a nitrile with LAH to the amine. Right, so if you reduce a nitrile or an amide, right, with LAH, you get an amine. All other functional groups, when you reduce them with LAH, you get an alcohol. So it's important to know, right, when you reduce all these different functional groups with LAH, what are you going to get? Okay. So we're going to be filling in some boxes here. So SOCl2 will convert a amide to a nitrile. And don't forget to, I'm just drawing out the CN as opposed to writing CN. It's okay either way. So you could just write bond CN or drawn out like I do. Okay. And we did not add or lose any carbons, right? So be careful not to do that. If you reduce an amide with LAH, you're going to get an amine. To convert a nitrile to a carboxylic acid, you either need to do an acidic or a basic hydrolysis. Okay, so either NaOH with H3O plus workup or just H3O plus. Okay, and of course we're gonna, if it starts with an amide or a nitrile, you have to heat it quite a bit to get that hydrolysis to work. And that's because the nitrile forms an amide, which then requires the heat to hydrolyze all the way to the carboxylic acid. Okay, to form a ketone, remember, starting from a nitrile, we can just use a Grignard reagent. Right, so we can just use the one that we need, okay, with an acidic workup, which is sometimes mentioned or not mentioned, unfortunately. And let's see what else. The nitrile reduction to an amine requires LAH. Right? Sometimes people will put in water as a second step, sometimes they won't. Okay, but same thing either way. Converting an amide to a nitrile is a dehydration, and it uses SOCl2. So be careful with SOCl2 because it can do a lot of different things, right? It can convert an alcohol to an alkyl halide. It can convert a carboxylic acid to an acid halide. And now you know it can convert an amide to a nitrile. So there are a lot of different reactions that utilize this as a reagent, right? So kind of make sure, sometimes when you're studying, it's helpful to group similar reactions together. And that way you're like, okay, I know everything SOCl2 can do, right? And that can be helpful. Okay, and then this is utilizing a Grignard reagent. So this ethyl group came from a Grignard reagent, but it's a ketone product, right? Normally when we use a Grignard reagent, we get an alcohol product. So the only starting material this could have been was the nitrile, right? So the nitrile will, I'll not draw it out this time, just write CN for you, either way, okay? And that's the only way we can get a ketone directly using a Grignard reagent. Because remember, with an acid chloride, you would have to use a Gilman reagent. So this one is kind of special. Okay. You can see my cat crawling through the windshield here. It's like, aren't you done yet? Okay. Say hello. Piper, you want to say hello to all the people? Okay, you can get down there. All right. All the 2 people that are attending office hours. All right. So let's do some synthesis. Okay, so we have an aldehyde and we're making an ester. So it looks like in terms of the carbons, right, I've got 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So I just need to reduce this to an alcohol. Right, so if I can get to an alcohol, then I will be able to make an ester, right? So that's kind of my process here. Then I just need to remember how to do it, right? So typically with an aldehyde or a ketone, we would just reduce with sodium borohydride, or LAH would be okay as well. And then to make a ester from an alcohol, you have 2 choices, right? You've got, oh my God, cat, you're killing me here. He's like, you gotta go out now. Okay. Otherwise, we're gonna start losing equipment pretty quick. Okay, so for this, we can choose the Fischer esterification if we want. We could choose you could have this have come from an acid chloride, right? So we've got some options. We could just use the acid chloride with some pyridine, right? That's one option. Or I could do a Fischer esterification. So I could have used the carboxylic acid and an acid catalyst, right? And then let's see. So it would be more work to convert this to an alkyl halide. So I don't think I would do that. But if I did convert this to an alkyl halide, then I could use sodium carboxylate, which doesn't make sense in this case, but you could do it. That's the 3rd method to produce an ester. Okay, and now looks like we're going to be doing some electrophilic aromatic substitution reactions. And we need these groups to be introduced meta to each other. And right now, both of these groups are orthopara directors. So we needed to have installed a meta director and then converted it later, right? So the nitrogen here could have come from an amine, right? So if we're kind of thinking backwards, and a lot of times retrosynthetic analysis is super helpful here, right? So we could maybe have gotten this from an aniline, right, through an acylation reaction. So basically amide formation. And then if I think about this, maybe the nitro group, this could have come from a nitro group, right? So kind of thinking backwards. The way you usually get an NH2 group attached to an aromatic ring would be from reduction of a nitro group, right? So now I do have a meta director in the nitro group, but I won't be able to introduce this after the nitro group because would involve a Friedel-Crafts reaction. So it might actually be better to have also had a carbonyl here, and we can figure out how to make this in the forward direction, right? So in the forward direction, I would probably introduce the acyl group first. Which is a meta director. And I am allowed to introduce a nitro group after that. No problems there. So nitric acid and sulfuric acid are the conditions to do that. Right. At this point, we need to reduce both the carbonyl and the nitro group. So we can do our Clemmensen reduction. And that will, with a basic workup to give us the free amine, we would reduce both of those, right? And then we just need to make an amide, right? So we could, the best is the most reactive of the carboxylic acid derivatives, which would be the acid chloride. Okay, and you could use an equivalent of pyridine if you wanted here as well to act as the base in the reaction. So this was kind of our retrosynthetic analysis, right, that helped us figure out retrosynthetic analysis. I spelled that wrong. Okay. All right. So moving on to the next one. We're starting with, oh yeah, go ahead.
Sorry, just for the retrosynthetic arrows, I thought they went the other way. Are they?
No, it's more like, oh, you know, I think they do put them
like this can be made from.
Yeah.
Sorry, just from
I think I just do my retrosynthetic and arrows differently. Yeah, okay. They might do them like this or something, right? I can't remember.
Yeah. Yeah. Okay. Sorry.
It's okay. I don't think it's a big deal either way. What arrow you use. It's not like a resonance arrow. It has to be specific to.
Okay.
Yeah.
I just thought I was like losing my mind.
It's not a particular important arrow. The idea is that you differentiate it from like a real arrow.
Okay.
Like one of these arrows or something. Okay. I'm curious now. Like, what arrows do they use? I have to look it up. Okay. So starting from an alkane, we of course need to do a radical halogenation. So this is going to be the same three-step process we've seen a lot of times here. And then we're going to eliminate. In this particular case, we should not use sodium hydroxide because that would give us the Zaitsev alkene. So we actually do want to use a bulky base. Normally it doesn't matter in the other cases that we've seen, but in this one it does. Right? because we need the Hoffman product specifically. And now we can introduce a group, and we could possibly make this through a Grignard reaction. So I'm thinking to introduce a halogen. That would give us a useful functionality at that carbon. And in this case, you could use the Grignard or the sodium cyanide method, doesn't matter. I think I'll just use a Grignard. That gives me a carboxylic acid, and then you use one of your methods to make an ester. Right? So because this is just a methyl group, it would be easy to use that first method where we treat with the base followed by a methyl halide, or alternate esterification reaction there. Okay. So this one also, same thing to start with. We're starting with an alkane. So we're going to do our radical halogenation. Now the goal is to get an alkene here, right? So we want to eliminate to now produce the Zaitsev alkene. So a small base would work well for that. And then perhaps we want to introduce another halogen. That would put a bromine at the less substituted position. And so this one is you could use sodium cyanide, but because it's secondary, the yield would probably be pretty low. So that's an option. Or you could do a longer approach and take a higher yield for all your steps, but it would take a lot more time to do it. So I think it's up to the chemist at this point. So either sodium cyanide and take a lower yield because it's secondary, or you do a longer approach where perhaps you want to get to the nitrile through a carboxylic acid derivative. So we could make a carboxylic acid, we could convert that to an amide, and then convert that amide to a nitrile. Right, so the conditions here for the last step is a dehydration with SOCl2. To make the amide, this is probably, the book teaches you a two-step process for this, where you would first have to make the acid chloride. There are ways to do it in one step, but not that the book shows you. So we would actually make the acid chloride and then react that with ammonia. And sometimes it says excess ammonia, depending on where you're looking at the reaction. And then to make the carboxylic acid, we would probably do a Grignard. So sometimes I work on it from the opposite direction too. So I figure out the path I want to take and then add in all the reagents later.